Hi guys! We are going to talk about 2 out of the 3 types of chemical reactions today. This snippet of information is directly from Module 6 if you want to refer to it. And we're going to be talking about precipitation reactions first and foremost today, which are essentially when a solid or precipitate forms from the combination of 2 solutions. We'll go through some examples, but when something is insoluble, using our solubility rules, this table right here, that means that it's a solid or it's a precipitate. In the state of something that's a precipitate is solid, S in parentheses, and that's really important because that tells us the precipitation reaction can actually occur because one of the products is insoluble according to our solubility rules. We look at neutralization reactions. These are also known as acid-base reactions, and it's when an acid and base react to neutralize the other. The products of an acid-base reaction are always going to be an ionic salt, or just a salt, plus water. And we'll see that in action. But a salt is just something that forms when an acid and a base react with each other. These tables on the right we're going to refer to. Our solubility rules are the defining rules for telling us whether something is a precipitation reaction or not. It's a precipitation reaction if the products on the right side of the equation are maybe one is AQ and one is solid, or maybe the opposite. This one is solid and this one is AQ. As long as one is solid, as long as one is insoluble. If both products are AQ, no reaction, no precipitation reaction occurs because no solid is formed. Let's look at an example here. Number 71. Complete and balance each equation. If no reaction occurs, write no reaction. And no reaction will occur if all of the products are soluble and none of them are insoluble and form precipitates. Lithium iodide plus barium sulfide. Our products form. The way to write a precipitation reaction is essentially, that is not my pen, is essentially flipping what pairs together. So the first ion of the first compound and the second ion of the second compound pair together. It's a little flip-flop there. And this is our product. Is this complete? Not quite, because we have to take account of the charges. If we look at the periodic table, we notice that essentially lithium is a +1 charge because it's in the first group. Sulfur is a 2- charge because oxygen is a 2- charge, and they're in the same group. If we bring these down, we know that lithium gets the 2- charge of sulfur. So it's going to be Li2S. The next product formed is barium iodide because those are the only 2 left, so they pair together. Then it looks like this. We're not done with the charges yet. Barium has a 2+ charge since it's in the second group. Iodide has a -1 charge since it's in the halogens, I believe. It's in the noble gases, the very last group, so it always has a -1 charge. If we're dropping down the charges, iodine gets that 2+ charge from barium, and it's Bai2. Let's look at these compounds. The first one is Li2S, and then we have Bai2. Let's determine whether they're soluble or not. If we find S2, S2 is pretty much always insoluble. There's some exceptions. When S2 is paired with lithium, sodium, potassium, or ammonia, it's going to be a soluble compound. Anything else is insoluble. So, we know that our first compound here is going to be an AQ, aqueous state, meaning that it's soluble in water. Barium iodide. Iodide is right here. When it is paired with silver, mercury, or lead, these are the only instances in which these compounds would be insoluble. When paired with anything else, we can see iodide is soluble. Right here it says it, generally soluble. So this is AQ as well, meaning it's soluble in water. Unfortunately, that means no reaction occurs because both are soluble and we get no precipitates, so no precipitation reaction occurs. So we don't need to worry about balancing it. If we look at potassium chloride and calcium sulfide in the next example, let's make our products. We know that these two pair together, the first and the last, and these two pair together, the first and the last again. Our products, Ks plus CaCl. Let's write the charges. Sulfur is 2-, like I said, because it's in the same group as oxygen. Potassium is +1 because it's in the first group. Calcium is 2-, it's in the second group. And chlorine is a -1. Let's drop down all the charges, which would give us a K2S and a CaCl2. Let's determine whether our products are soluble or not. Looking at S2 right here that's already circled, it's normally insoluble, but when it is paired with lithium, sodium, potassium, or ammonia, it's soluble. So K2S is an AQ state. Calcium chloride, let's look for chloride. It is pretty much always soluble unless it's paired with silver, mercury, or lead. And calcium is not silver, mercury, or lead, so it's soluble. Hence, both of these compounds are soluble. Not off to a good start. Does a reaction occur? No, it does not, because none of our products are insoluble. None of them are in the solid state and form a solid. But let's do C as our last one. Okay, we have chromium bromide and sodium carbonate. Let's do, again, the flip-flop rule here. Chromium and carbonate are going to form a compound, sodium and bromide. And now let's write our products. We have CrCO3, chromium. In this case, we can see the bromide has a 2, which means that's the charge from chromium because it was brought down. So chromium is a 2+, and carbonate is a 2-. The charges cancel out since they're the same numbers, so it's just chromium carbonate here. The next one, we have sodium bromide. Bromide is a -1, sodium is a +1. Those cancel out as well. We have NaBr. Let's look at our products. We have CrCO3 and NaBr. First, let's look at carbonate, which we know from the table is pretty much always insoluble except for some exceptions. And the exceptions are lithium, sodium, potassium, and ammonia. We have sodium. Oh, no, we don't. We're paired with chromium, and that's not listed as an exception, right? So that means that it's going to, by default, be an insoluble compound that's in the solid state. Sodium bromide. If we look at bromide minus, Br minus here, we see it's pretty much always soluble. There's some exceptions, and the exceptions are silver, mercury, and lead. Since sodium doesn't fit under that, it's by default going to be soluble. Our products formed here, this is going to be, I already forgot, it's going to be solid. And this is going to be AQ. Does a precipitation reaction occur? Yes, it does. We know that because one of the products are insoluble. This is our precipitate. It's a solid in water. It falls out of the reaction. This is aqueous. It dissolves in water into its respective ions. and a reaction does occur. For the sake of time, I'm not going to balance this since we reviewed that in another module, and I'm going to move on to explaining acid-base equations. These are really straightforward, and I like them because there's a general pattern to these, and I will show you what that is. You can see that these have the aqueous state because they dissolve into their respective ions in water, and it would look like Ca2 plus would be dissolved in OH minus, and H plus and SO42 minus would be floating around in water or in the solution, whatever it is. In order to kind of complete these equations, we always have acid. This is going to be our template plus base makes water plus our salt. And we can go ahead and write out water from the get-go because we know that's always going to be the product of an acid-base equation. The salt is what we kind of did for our precipitation reactions, and that's pairing kind of the opposite ions in the different compounds with each other. So if we look at this, in this case, we would be pairing SO42 minus and calcium together. Why wouldn't we be pairing like SO4OH minus together? First of all, we don't have a compound like this. We have to have a lone ion, a lone element in the product. The other two that form, we know, are water. And this is always going to be the case. You can always rely on pairing two ions up with each other to form water. If we look at what our other product is, which is the salt, it's going to be calcium CaSO42 minus. Since sulfate has a 2 minus charge, and so does calcium, they cancel out and we just get CaSO4. I'm not going to balance this for the sake of time, but this is the template you can go by. A salt is basically just an ionic compound that, can dissolve in water, and it also is always the product of your acid versus your base. For B, let's do this one really quick. The way to determine whether something is the acid versus base, in this case, it's not super important that we know which one is which, but for the future, something with OH or hydroxide is always going to be a base, for the most part. And then that we see that something with an H plus in here is usually going to be an acid. So that's just your rule of thumb for right now until you get into some exceptions in the fall. But let's look at what our products are. Our product is always water of an acid-base reaction. In this case, what forms water on the right side? We have to kind of look at that first. OH plus a single H makes H2O, right? So those are ruled out. Those aren't a part of our salt because those form water and we need water in the products. What's left that doesn't form water is what's going to be in our salt, and that's potassium and chlorate. In this case, it's KClO4. Sorry, this is perchlorate, I believe. Potassium perchlorate, if I have that right. Water is always a liquid. Okay, so you can just kind of, by default, write that L right there. And then your salt dissolves in water because it's an ionic compound. Oops. So you can always, by default, write the AQ, and you need those phases in there. That's important. Wrapping up the acids and bases reactions, this is your strong, weak acid and bases chart that you'll see in your textbook in the fall. Have these memorized, have these known. Notice that everything pretty much with hydroxide is pretty much a strong base. These are all strong bases. And not all of these are strong acids right here. Actually, these are all strong acids. These are the weak acids that you need to know. There's more, but these are some of the most important ones. And then this is a weak base because clearly it doesn't have OH in it. Thank you guys so much for watching. This was precipitation and acid-base reactions.